In this video, we'll look at how we can apply our knowledge of transformed sinusoidal functions, that is, sine and cosine functions, in solving word problems. And we're going to look at two very typical word problems of this type, the Ferris wheel problem and the tide problem. First, let's start with a Ferris wheel problem. A passenger rides on a Ferris wheel 16 meters in diameter. The bottom of the wheel is 1 meter above the ground. The wheel makes one rotation every 24 seconds, and at the start, time is equal to 0. The passenger's at the bottom of the ride. First, we're asked to draw a graph of the height of the passenger above the ground versus time. So my y-axis here is going to represent height, and my x-axis is going to represent time in seconds. And before I try and draw the graph of height versus time, I'm actually going to draw a rough sketch of the Ferris wheel. If this is the Ferris wheel, I know that the bottom clears the ground by 1 meter, and that the hub at the center is 8 meters from the circumference on all sides. That's going to allow me to label my y-axis here, because I can pull each of these points across. The lowest that the passenger is going to be is down here at 1 meter. The highest they're going to be at the top of the Ferris wheel is a total of 17 meters above the ground, and when they're in the middle of the ride, they're going to be 9 meters above the ground. I'm going to draw a horizontal line across here from height is equal to 9, because that's going to represent the axis of my sinusoidal function. I'm now going to consider what's going to happen to the person as the ride goes around. Their height will follow a sinusoidal path as they go round in a circle around the Ferris wheel. In other words, their height is going to describe that kind of relationship against time. We know that the wheel makes one rotation every 24 seconds, so we'll put 24 there. Halfway through that, they'll be at the top of the ride, that's 12 seconds. Halfway through that again, we'll be at 18 and 6, we can label those there. So we know that height versus time is going to look like this if we start at the bottom. Next, we're asked to find an equation for the height of the rider above the ground as a function of time. And we're going to use the graph that we've already drawn to help us do that. We're looking for h as a function of t is equal to something. And we're going to think about how we can transform either a sine or a cosine function to get the graph that we've just drawn. If we go back and look at the graph, we can see that it looks like a flipped upside down cosine function. Usually a cosine function starts at a peak and then proceeds downwards. This one starts at a trough and proceeds upwards. We could pick a sine function because it's also a sine function if you look here starting at 6. But the nice thing about picking a cosine function is we won't have to do any horizontal translations, and that makes things a little easier. So I'm going to think of this as an upside down cosine function and think about all the other transformations, in addition to turning it upside down, that I would need to apply to that cosine function. And the way I'm going to do that is by thinking about the amplitude and the axis, as well as the period of that function. The amplitude of the function, if we look back on the graph, is 8. That's the radius of the Ferris wheel, and that's the amplitude of that cosine function. The axis, the line that we drew, is the line h is equal to 9, or you could think of it as y is equal to 9. The period is 24 seconds. And we know that the period has to be equal to 360 degrees divided by the b value that goes in the function. So if I rearrange this, I get b is equal to 360 degrees over 24, which is equal to 15, and I'm going to leave the degree sign off for now. So with all of this information and thinking of that graph as an upside down cosine function, I can now proceed to write an equation. I know that the amplitude represents the vertical stretch factor, so if I put the negative in front, I need -8, and then cosine. I found my b value, 15. There's no phase shift, no horizontal translation. That's why I chose the negative cosine function, to avoid horizontal translation. So I just put my t in next. And then I have to shift the whole function up by 9 to get a new axis of h is equal to 9. So there is my new transformed function. You could think of this as y is a function of x, or just y here, and the t is x. Swapping out the variables doesn't make a difference. I've just chosen h and t to make them fit with the word problem. The next thing we're asked is to find how high above the ground the passenger is at 1 minute and 2 seconds to one decimal place. Essentially, we're being told when t is equal to 62, because remember t is in seconds, what is h equal to? And h is a function of t. So this simply involves plugging 62 into the function that we've just worked out. So h of 62 is equal to negative 8 cosine of 15 times 62 plus 9. And now we just plug this into our calculator, and you can do that all in one step. Make sure that your calculator's mode is in degrees. And you should get that h is approximately equal to 15.9 meters above the ground. So at 1 minute and 2 seconds, the passenger is about 15.9 meters above the ground. So that's an example of a Ferris wheel problem. The approach that we took was to draw the graph from the information by first drawing the Ferris wheel to the left, then sketching the graph, figuring out what the amplitude, the axis, and the period are, and using that to come up with an equation. Then we could use that equation to solve problems like we were given at the bottom here. Let's look at another common type of problem, the tide problem. We're told that the depth of water in a harbor over a 24-hour period is given as shown here. We're given time evenly spaced in increments of 3 hours, and the depth as shown in the bottom row. Now, if you look at the values for depth, you notice that they seem to oscillate around a midpoint of 8 with a minimum depth of 1 meter and a maximum depth of 15 meters of water. So we could sketch that out right on top of this row as following a pattern kind of like this. And I'm asked to sketch a graph to represent the depth of the water versus time over a 24-hour period. So depth in meters will go on the vertical, the y-axis, and time in seconds will go on the horizontal, or the x-axis. I know that the minimum depth is 1 meter, that the maximum depth is 15 meters, and 8 meters is in the middle. And I can follow this pattern to try and draw a rough sketch of the depth over 24 hours. And at the end of 24 hours, I'm back down to the axis, right about there. So that should be 24 hours. 12 hours should be in the middle at 8 meters, so that works out there. And I can find 15 meters as a minimum, 3 meters is another minimum, 6 meters goes here, 9 there, 18 is a little bit off, but should be there, and 21 there. So that's not great, but a rough sketch of what's going on over the 24-hour period. Next, we're asked to find an equation to represent the depth of the water as a function of time. And as we did previously, we're going to first consider what function we want to use as our parent function, and then the amplitude, axis, and period are going to help us find the equation of the function. If we look back here at our graph, the simplest parent function to use would be a negative sine function, or rather a sine function that's been vertically reflected, because if you look here, you see an upside down sine function, a sine function that's been vertically reflected, and choosing that is going to allow us to define our function without having to use a phase shift or a horizontal translation, and that always makes things a little bit easier. So I'm going to start with the idea that I'm going to be using a negative sine function. Now let's think about what the amplitude is. Well, the amplitude, if we go back, goes from the midline or the axis to either the peak or the trough. That's going to be 7. So the amplitude is 7 or 7 meters. The axis, we said, was the line depth is equal to 8, or you could think of that as y is equal to 8 if you prefer. And the period is 12 hours. And we know that the period, 12 hours, has to be equal to 360 degrees divided by the b value that goes in our transformed function equation. Rearranging this, I get b is equal to 360 degrees over 12, which is equal to 30. I'm going to leave the degrees off for now. That means that I can write my function as depth as a function of time is equal to, remember we said we're going to use a negative sine function, so negative, then we incorporate the 7 for the vertical stretch factor to get the right amplitude, sine, and then I need my b value of 30, my independent variable t, plus, and then a vertical translation of 8 to give me the new axis. So depth as a function of time is equal to negative 7 sine 30t plus 8 describes the function that we drew. Now that we've got this equation, we're told that a ship requires at least 4 meters of water to enter the harbor safely, and we're asked, is it safe for that ship to enter the harbor at 1600 hours? Remember, we started the clock at midnight, so 1600 hours is time is equal to 16, and we're therefore being asked, what's the depth equal to at that time? Well, if d as a function of t is equal to this, we can just plug 16 in for time. So we're being asked, what is the depth at 1600 hours? And that's going to be equal to negative 7 sine 30 times 16 plus 8. Again, you can plug this all directly into your calculator. Make sure that your calculator is in degree mode, and you'll get that the depth is approximately equal to 1.9 meters. And that means if it needs 4 meters of water to enter safely and it's only got 1.9 meters, then no, it's not safe. So that's an introduction to word problems of the Ferris wheel and tide variety, very common types of word problems that you'll see with trig functions.